you zoom on the board more?
Okay. So get us back up to speed to where we're at before. Remember that we're working with some psych and law data here. All right. And what we're looking at is we want to put together a logistic model that's looking at predictors of whether or not people receive life in prison or death sentences. Okay. And so our outcome is a dichotomous sentencing variable. Life is our reference group, death is our criterion. And our predictors here are a number of victim impact statements introduced by the prosecution, a subjective depravity score for the homicide, like how gruesome and terrible this was, I guess. And then also wanting to look at mode of delivery for this victim impact statement. We've got 4 different types here, right? So what we've got is we've included a categorical variable into this model as a predictor. Okay. Now can we just throw categorical models or categorical predictors into a normal regression? No, that doesn't work. And really you can't actually do that here either. You still have to dummy code them up. But there's some different stuff that you get with this that's pretty cool. So we've got a categorical variable here, 2 variables that we're treating as continuous, and then some dichotomous outcome for our binary regression model here. Okay, so we went through and we took a look at our 2 in terms of our screening. Once you took a look at our 2 predictors that we're treating as continuous. So number of victim impact statements is not continuous. This is a count variable, right? Which introduces its whole sort of line of things, and there are whole different models that better handle count data. But we're going to ignore this. We're just going to treat it as a continuous variable. But this is typically what you see with count data: a lot of zeros or something that's quite sort of infrequent, and then things kind of pushing out. With victim impact statement, everything looks kind of like a nice skewed distribution. We got someone who's applied 14 victim impact statements, which is over double what sort of the next highest piece is here. Okay, so we're thinking we probably need to do something with that, right? And then we go down through and we take a look at our depravity score. Again, something that's a little more kind of sort of pushed out here, but we've got kind of a more of a tail that kind of trails out. Okay, now remember, one of the reasons that we really like logistic models is we don't have any assumptions about the distribution of our predictors. It's nice if they're normal, tends to lend to a nicer and kind of tends to be maybe a more powerful analysis, but they don't have to be normal. It doesn't screw things up like it does for our continuous regression models. So the fact that these variables are not, the fact that they're skewed doesn't really bother me all that much. But what does bother me is the potential of like a big outlier. Outliers can still mess with your model, right? And so, you could think like, oh, how do we address this? Do we get rid of these cases? Well, I don't want to get rid of these cases because they represent kind of the extreme of what would happen. So I still want to have them sort of in place. Do I want to try and transform everything? No, because that's a whole lot of stuff to deal with, try and get like 1 or 2 people. And so what we elected to do was go through and smooth, okay? And we used a little bit different approach for both of these. And Haley and Olivia like neither of them because it seems like just making up new data to put into your model, which is an understandable reaction, okay? Smoothing is one of these things where we're just saying like, hey, here's a value, a score for somebody, and we're just gonna plug in a different score, right? It's kind of an old school method and something that, but I mean, it's not really any different than a mean substitution, like where people used to just dump the sample mean in for a missing value. You're just like straight up making up a value for that person. You don't know whether it's good or not. Now, we don't do that in terms of like dropping sample means into things. At least you do know after you've gone through and checked these, at least what these are. And so what we typically would do is go through, and what we did for the number of impact statements is we just assigned this most extreme case to just be 1 unit higher than the rest. So what we did is we went through and assigned this a score of 7 impact statements, right? We know that they didn't have 7 impact statements, but it's a big sample. What it does is it retains this person's rank order in terms of the overall set, okay? Now, we go down through and look at depravity score, took a little bit different approach here, right? So what you could say is, well, we can go through and set this to a score of 50, next highest score is 49, we're just gonna set this to 50, could do that, right? But then you still kind of have it doesn't, with the previous one, if I smooth this, it addresses that tail. There's nothing else there. It just sort of puts that up against the rest of the distribution. Here, I can set this score of 70 or whatever it is here. I can set it to 50, but I still have this group of scores, this cluster of scores. Then do I take the whole cluster of scores and move that in? Now I'm moving a whole lot of scores. And so what I elected to do for this set is to take this in and move this to 60. And my rationale was like, well, here's a set of scores that's about a little ways off. And maybe if I move this in, it's at least less far out, but it's kind of equidistant from the rest of the distribution. So we've got kind of a spacing thing going on here. This is completely made up by me, right? Like it's just sort of me just kind of thinking about like what makes the most sense. Now I could go through and pull this all the way in. We could go through and do that. I actually went through and ran that. It doesn't make it that much better if I just pull it all the way in, right? If you look at skew kurtosis values and things along those lines. And so what I'm saying is just bringing this in and setting this at 60, so it's still out there. It's just not as far out there. I think this ends up being a z-score goes from like 5 something to 8 or something along, or excuse me, not to down to 4. It's still an extreme value. It's just not quite as far out there as it otherwise would have been, right? And so for me, I'm saying like, okay, I can live with that. I'm saying that's fine. But the thing is, the important thing with all of this is anytime you do something like that, you need to be very clear with your readers, like what you did and why, okay? Because it is just making up scores for people. You're bringing stuff in, but at least what I've gone through, I've done this, I've told my committee, I've told the reviewers, and if they don't like it, I can do something different, right? Hopefully what I've done to that thing is not going to sort of completely, hopefully with this case, if I set this to 50 or 60, hopefully that doesn't completely change the whole pattern of results that I've got. If it does, then it's a problem. And then maybe I need to think about whether or not I can keep that. If this one case completely, if what I do with this case completely changes the whole story, I need to start thinking about whether or not I can have that person in there or not, okay? But this is what we decided to do. So in the set that you have right now, open, you'll go through and see that in addition to a lot of other stuff, I just kind of moved around in there. But we've got number R and depravity R. These are going to be the cases that we went through and smoothed. Okay. People comfortable with this, what we did, and at least sort of the rationale behind our decisions with this? Okay, cool. So next thing we need to do is we're saying, all right, we fooled around with our continuous predictors. What we need to do now is go through, because we have categorical predictors. Remember that one of the things with logistic regression, we need to make sure that we have adequate coverage. Adequate coverage means that if I go through and look at sort of all the different cells and all the combinations of my categorical variable outcome with my categorical predictors, that I've got enough coverage. I don't have weird open cells or people who aren't represented within stuff, okay? So what we're gonna do is pretty easy to do. I'm gonna go up to Analyze, Descriptives, go down to Crosstabs.
Josh, should we have in our data set like the number R and gravity R?
He uploaded it into the handout section and not the data.
Oh, whoops, I'm sorry.
I was like, I think supposed to be running handout.
See.
Okay, yeah, I'm sorry about that.
Yeah, it's called like reverse.
Yeah.
Thank you.
Thank you, Olivia.
Oh, okay.
I see it.
He's uploaded this version into the handout and not the case. Yeah, I have that right. It's supposed to. I was gonna start when I know. I was like,
Yeah.
I'll fix it up because I went to open up something. Yeah.
People have sets open.
Yes, there we go.
Lindsay, did you get it open?
Yeah, I got it. It's just slow, but yeah.
Okay.
It's opening.
Opening process. Okay, cool. So what we're gonna do is we're gonna go to crosstabs, okay? And this is just gonna give us our crosstabs table. What I'm gonna do is I'm gonna go and I'm gonna put sentences into rows and then VIS delivery is gonna be my other categorical variable here, okay? So I'm just gonna go here, and then I'm gonna go through in terms of statistics. Don't need anything there because I'm not gonna run a statistic on this. But if you wanted to run your chi-squares or things along those lines, this is where you would find it, right? In terms of cells, what we do want to get is our expected value, right? Remember, because we've gone through and talked about our chi-square analysis is a comparison against our observed versus our expected. This is just telling SPSS to give us expected counts for our individual cells. And then that's all we need to do with that, okay? So you're gonna go through, hit paste. If I run this, I'll get the following output. I'm just gonna put it up here because it will be easier to see. Okay. So as I'm going through, this is what I'll get in terms of my table.
I'm sorry, this is still, are we like in actual analysis now, like in terms of, or is it still screen?
No, this is still screening.
Okay,
We're still screening with this, okay? Remember that for our logistic model, right? I want to see that for when I'm looking at the cross tabulation of my outcome with any categorical variables that I have in my model, I want to see that expected counts for all cells is greater than 1. And then I want, or excuse me, greater than 1, and I want to see no less than 20% of my cells with an expected count less than 5. Okay, so there's a couple of different things that we're looking at here. And again, with our logistic model, what we don't want is just big holes in our data, basically 0 cells coming in. So going through, if we look at this table here, we have our counts and then we have our expecteds, right? Daniela, do we have any expected counts that are less than 1 in this? Or 1 or less?
No.
Nope, right? So we've got decent coverage. Again, what we're looking for here is, let's say that no one who got the death penalty had an open VIS, right? If that was the case, that's problematic because I don't have any way to estimate that because there's no one who actually fits in that space. Okay, so none of our expected counts are less, or all of our expected counts greater than 1. Do I have any of those expected counts that are less than 5? Yeah,
Well, I'll answer that
Okay,
question
yeah.
first and then I'll ask my question. No,
No, okay. So in terms of coverage for our logistic model, we're in a pretty good place, all right? This starts to get tricky. Two things can happen, right? When you're going through and planning these models. It's really cool to be able to have categorical variables in here, but two things that can really start to screw things up is if I have a categorical variable with like 7 different levels, all of a sudden I'm gonna have holes in that data, particularly if I don't have a large sample size. I have to have a sample size that's large enough to cover and make sure that all of the cells in my table here are filled up. Yeah.
what I was gonna ask though is when we create this like cross tabs thing, does it matter which one's like the row versus column or?
Doesn't matter which one. It's just, the only thing you're doing is just to get counts in this and go through and take a look at it. Yeah, Olivia.
I get the reasoning for why we don't want it under 1, but what was the reasoning for 5?
It's just the rule of thumb that's used with chi-squares too. In your chi-square model, the kind of rule of thumb is you don't less than 20% of your cells have expected value of less than 5. It's just I don't know exactly the math on it. It's just kind of a rule of thumb for chi-squares and in these types of models as well. Yeah.
It's a rule of thumb, would we want to mention the one that has 6 in it?
What's that?
Since it's a rule of thumb, would it be worth mentioning the one that has only 6? Count of 6.
Yeah.
Right,
Probably not, because again, it's how many cells we've got here. We've got 3 by 4, so we've got 12 different cells, less than 20%. 12 is close to 1, 2, 1.5. Yeah, so like 2 to 3. So even if you had, this is low, but it's even if that was 4, you'd still be all right. Okay. I mean, you can think about this as sample size. You want representation within each of these cells, right? I mean, it's not great, but we've got a pretty big table here with 12 different cells, right? So again, thinking about as you're setting these types of models up, always remembering that if I'm going to have a lot of different categorical variables, you're going to have to plan to increase your sample size and make sure you got adequate coverage. Okay. Questions about this? Okay. Cool. So we're looking good here. Now the other thing that we want to think about, and if you remember, we talked about the linearity of your logit, right? Logistic models are nonlinear models, okay? But what we're doing is we're taking this probability function and we're turning it into a log odds, because log odds do hold a linear relation with outcomes. And so what we need to do is make sure that we don't have nonlinearities in that logit, okay? Which seems like kind of a hassle and a big thing to go through. But fortunately, at least within SPSS and SATA 2, if we wanted to go through and chase that down, I'm sure R does anything, so you can probably get it figured out. Actually, a pretty easy way to go through and do this. So what we're going to do is I'm going to go up and go analyze descriptives, and I'm going to take a look at my 2 variables that I smoothed here. Okay. So I'm going to take a look at number R, depravity R. Okay. And what I'm going to do is I'm going to go through, take a look at my mean values for each of these, and I'm going to go through and I'm going to center. Okay. We go. Compute. C. Impact R. Going to be equal to number R minus 1.4309. This PSS syntax is a little rusty, but I think that'll do it. Okay. And I'm gonna go through, I'm gonna change centered deprav or turn that into gravity R. Okay, you're just going to center these two variables. We'll check this to make sure that did it right, which is always a helpful thing. Means of zeros, so looking good. So I got these centered appropriately. Okay. Now, again, the reason I'm doing this is this is just like any other measure, like any other type of regression. Centering your continuous predictors is just kind of good plan. So we just got that out of the way already. But what I'm going to do now, in order to check the linearity of my logit, I'm going to go to analyze, and I'm going to go to regression. I'm going to go down to binary logistic. And what I'm going to do is I'm just going to start building a logistic model where I've got my dependent variable is sentencing. Okay. And then what I'm going to do is I am going to enter my centered impact statement, centered depravity. Oh, whoops, forgot a step. Cancel this for right now. I've gone through and created my centered variables. I forgot. Now what we need to do is I'm going to go through and I'm going to run a natural log transform of both of these. So I'm going to go to analyze, or excuse me, transform compute variable. I'm going to call this variable ln impact. And I'm going to set this equal to the natural log of 1 plus ln r, right, or number r, yeah. Okay. So what I've done is I'm creating a log transform of my number of impact statement variables, or my number of impact statements. Okay. So then I'm going to go through and I hit paste, changing this. I've already got this in there. This is fine. Okay. Then I'm going to copy this. Yeah, Kate.
Why are we log transforming?
Hold on to that.
Okay.
Okay. So you go through, take a log transform, and take a second one, call this log transform of depravity. We're going to set this equal to 1 plus depravity R. Okay. And then I'm open up RR. Okay. So what we need to do is make sure that we do not have violations of our assumption of linearity of our logit, right? So what we're going to do is we're going to go through and we're going to center our variables, make sure that those are centered. But then what we're going to do is we're going to run a logistic model where we have our continuous predictors in the model, along with our continuous predictors times the multiplied times the natural log of that predictor. Okay. basically what this is it's a hack to go through to test the linearity of your logit, right? What we're gonna do is hopefully that none of the interactions, none of the interaction between our continuous variable and the natural log of that variable comes up as evidence for an effect. If we do, it suggests that there's a nonlinearity going on in there, okay? So basically what we're doing is we're gonna run a couple of moderation or run a moderation model and hope it comes up empty on stuff, okay? Tabachik and Bell have a great chapter on this, or not on this, but on logistic models. Again, would encourage you to go through, read through that. This is a pretty slick way. Same thing with Kate with our leverages, where we go through and we want to back, okay, I've got some high leverage values. I want to figure out like what combination of things is causing this to be a high leverage. So I go create a dummy that just identifies that one case, and then I just regress that dummy onto all of my predictors to see what comes up as the predictor. The model itself doesn't mean anything outside of just giving us a flag to whether or not we've got a violation here, okay? But the nice thing is once we've gone through and we've done this, for our the package in SPSS, if I go to regression, binary logistic, okay, I'm gonna go through, I'm gonna put sentencing in my variable here, okay, and then I'm gonna have my centered impact and my centered depravity score. So we're gonna drop those two things in there, okay. And then what I'm gonna do is I'm gonna create an interaction of the natural log of my impact plus or multiplied by my centered impact score, okay? So I'm gonna go through and in our logistic model, if I go through and I find my centered impact, I hit shift, I believe, and natural log of impact, no, there we go, hold down control. Okay, so if I go through centered impact, and then I hit control and I hit natural log of impact, it should highlight both of those. People get that? And then if I hit this A times B button and move that over,
That's very cool.
yeah, I don't know why your standard regression thing doesn't do that for you.
Yes.
It's one of the things like that's really slick about like in Stata, like with stuff like you just hashtag two variables together and it will go through and do it all for you. I don't know why SPSS won't do this. It's done it forever in your logistic thing, but it makes it a lot easier than actually having to crank out your stuff. Okay.
When you do this, does it actually like create a variable in your data set?
Nope.
Okay,
Nope,
interesting.
it just goes through and does it, right? So same thing, gonna get click on depravity, control, natural log of depravity, drop that in there. Okay, so that's looking good. And then I'm gonna go through, last variable in our model is BIS delivery. Okay, so just making sure we have our full model. We're just gonna run the model that we're gonna run anyway. We're just including these two interaction terms. Okay. And then because we don't really care about anything outside of just testing these interaction terms, that's all we need to worry about here. Okay. So we go through and run our model. Oh, whoops.
Here's just one extra thing.
What's that?
Your screening output handout thing has a contrast line in it.
Oh, yeah, that's what I'm fixing right now. So if we go to back to regression, go to binary logistic, the one thing we have to do for BIS delivery, what we need to go through is hit categorical, and you gotta tell SPSS that BIS delivery is a categorical variable. Otherwise, it's just gonna treat it as a continuous outcome, okay? And now what we need to do is go through. Sorry,
Where do you do that? Sorry, no problem.
Click on category.
on categorical up here. Click that, and then just tell SPSS that BIS delivery is a categorical variable. Okay. Now, when we actually get into our model, it doesn't matter here. What you'll see here is you've got different ways it can go through and code. This is a categorical variable, and you need to really make sure that you know who your reference group is with this stuff. For this, we don't care about it because we're just dumping it in there to get an output, but this is where that contrast thing came in. You're gonna go through, continue that, paste that piece in there. Get rid of that. And run this. Okay. So now if we go down through. A little bit different than. What's that?
Rent, the second group of compute, like,
These ones?
yeah.
Yeah, I already had those in there, so I don't.
Mine also, like mine matches yours, what you
This
just,
matches the,
mine doesn't match the
Matches
the screen.
Yeah.
Say, mine matches what you just did.
Okay, maybe does yours match that?
mine matches, the screening of the paper. That you uploaded.
Mine does not match the screening on the paper.
That's what mine's. No, now it does.
Wait, how?
I don't know. So I didn't go through and run that, the natural log. That I had set
So
up.
I guess I haven't either.
Yeah, okay, so go through and do that, and it will, I don't know, I guess there was
You had miscalculated your natural log.
something in there, yeah.
What? Just rerun the natural log. Cause even though we already have the variable.
Yeah, there's something screwy with the natural log. Okay. So, going through, taking a look, main thing here, the only thing we're concerned about is taking a look at p-values for our interaction variables here. And Haley, does it look like we have any evidence for violations of linearity in our budget?
I'm looking at the,
P-values for your
variable.
interactions.
oh, okay. Yeah, I guess delivery, like, which I'm assuming we coded as 0, is that like right at 0.046?
Okay, so no, just your interaction.
Oh, just the interaction,
Yeah.
no.
Okay, no evidence here, right? So again, a really quick and easy way to go through and see whether or not we have evidence for a violation of our linearity or our logit, right? So all we're doing when you're doing the screening is you're just taking your continuous variables, right? And creating an interaction between your continuous variable and the natural log of that same continuous variable. Create an interaction term, go through and throw that in the model that you're gonna run and just make sure that we don't have anything pop up, right? And honestly, if you did, then you've got a whole situation to go through and figure out because that's kind of a mess. It's happened to me before. I can't exactly remember how I solved it. But don't worry about that for right now. So just sort of know that we need to go through, kind of take a look. You can still like run it, but it's not actually, you're worried about it. It's not sort of 100% getting as strong as effect as you would, because there's potential non-linearity going on there that you have to chase down and things along those lines. But for our purposes, we're just take a look at going through and identifying it. Okay. So people get how we're going through and testing this piece of things.
So the purpose of doing the logistic regression during the screening for this is to just look at if there's any violations of the
Yeah,
linearity of
that's it.
logit, okay.
That's it. So you're not looking at this for anything outside of p values associated with those interactions to just see if you have any evidence for non-linearity. Think about this as kind of like if I were to regress, if I had a continuous variable, and I multiplied that continuous variable by itself, see if that predicted an outcome. That would be essentially saying the square of something was predicted for your outcome, which would suggest a non-linearity there because that's essentially giving you a shape. Same thing we're doing here. It's just instead of the thing by itself, it's the variable multiplied times the natural log of itself, right? So the only thing that you want to make sure, remember when we were going through with that, with those, when you're calculating the natural log of your variable, notice here on our handout, we're taking the natural log of our original variable, not the centered variable, because 0 is going to be dead center in the middle of that centered variable, and you can't take the natural log of 0, and that's going to screw things up, right? So making sure that you're doing your and then taking a look to make sure that, I mean, it never hurts to add 1 to whatever your variable is. If it just, you have a 0 point on that, you just can't take the natural log of 0. So just keep that in mind as you're going through and constructing. If it starts throwing errors at you, just make sure that you don't have 0 in terms of your output. Okay? Or 0 as a value on your score. All right, questions? Okay. Last thing we're gonna do, just real quick, is we're gonna go through and go analyze correlations, bivariate, and here we're gonna look at our centered impact, centered depravity, and that's it, because those are just our two continuous variables. We're just going to go through, make sure that we don't have any collinearity or redundancy going on.
Yeah, just in your handout, you had the non-centered variables. I don't know if there's a reason for that.
No, it doesn't matter. So, yeah, the centering won't change the linear relation there. Okay. So going through, any concerns with linearity here? No, right? You got correlation 3 where these two things seem to be pretty much independent of one another. So we're good. So going through and taking a look at what we end up with. Okay. Accuracy, plausibility, no evidence of problematic values, right? Now, maybe with the BIF of 1 billion and the depravity score of 1 million, maybe go through and check those to make sure that those are real cases, right? Or real values, but there's nothing that is technically out of bounds in terms of our data, right? We don't have any missing values. So we're looking at the full sample of 122, right? We're gonna go through. We don't have any assumptions about the distribution of our predictors, but we still want to take a look at them just to kind of see what's going on, see if that's telling us anything about the variables that we're measuring. I want to make sure that we don't have weird outlying values and things along those lines. And again, remember that even though we don't technically have assumptions about the distribution of our variables, our logistic models just work better if things are multivariate, kind of normal. So we'll just go through and take a look. What we're seeing is BIS, this is a count variable. Clear violations of normality, histogram positively skewed with distribution for a single value of 14 falling away from the next highest value of 6. Box plots identifies sort of this ID as extending beyond 3 times the inner quartile range. Right, so we've got something that's an extreme value here. Same thing, depravity also non-normal, reasonably symmetric distribution, except with a set of cases with scores exceeding 40. Here we're identifying 3 cases extending beyond 3 times the inner quartile range, right? So we've just got some stuff going on with these. Sentence reasonably balanced. So we've got so no case split between life and death sentences in this set of individuals. frequency for VIS, delivery unbalanced. In terms of none, private, question and answer, and open. Okay. So again, just doing the same thing that we've always done, just accounting for our variables, right? Univariate outliers, case here, extreme value with a score of 6. And here's like the X value is 14, right? So like saying what's going on there. Got another 2 cases for depravity who are registering extreme scores, Z value of close to 7, Z value of 4. So what we do is we say smoothing procedures for both of these, telling what we assign for each one of these cases. Then going back through, taking a look at the resulting distribution. We're going to call it acceptable. I don't think that's supposed to be a skew of 11. That's a typo. Depravity is notably skewed and kurtotic, which again, we're just noting it. It's not necessarily problematic. We just wanted to say, like, this is what's happening in our data. Okay. I'm going to say we're going to proceed with the analysis of smooth scores, continue to monitor potential influence of case with high depravity. Coverage, this is easy. This is just our table, right? Frequency, expected frequency of all cells greater than 5, right? And if they're all greater than 5, we're assuming that nothing's less than 1. So just go through kind of shortcut there. Linearity of my logit interactive effects between continuous predictors and its natural log. They'll indicate non-linearities. So we're good there. Yeah.
In the coverage section.
Yeah.
Let's say you had like 10% of cases be less than 5. Like obviously that's not like violating like our assumptions, but would that be something you would mention?
I
in
might,
screening?
yeah, just to kind of say like, we don't have a problem with coverage necessarily, but it might be kind of thin. You say like we've got like 2 cases with expected values less than 5. So again, this whole process is if something goes sideways down the road, we can go back through like, okay, this gives us a place to start. Is there something weird going on with this group? Because essentially, it's like you can think about this as running a t-test with less than 5 people in a group, right? There, you just don't have that many people there to compare against. Yeah, Joe.
Do we still do like the leverage?
Don't need that. I mean, you could if you wanted
I don't want
to.
to.
That if you, I mean, there are versions of that you could get into with the logistic, but the nice thing about logistic is we're doing all of that because there's assumptions about your residuals and sort of the structure of that. The really nice, the thing that makes these logistic models nice is they're pretty robust. You just kind of, like an old pickup truck, you can kind of kick it around and it kind of keeps running, like you can throw stuff that you shouldn't throw into cars into it and it still just kind of runs, right? So they're really nice in that way. Continuous predictors, near no correlations in these data. So we're good, right? So saying VIS is a count variable, heads up with that. VIS and depravity both have extreme scores, violations of normality. Representation in delivery is not balanced, right? So we're just saying, while we don't have formal assumptions, extreme values are potentially problematic in those cases. Technically, we're modeling number of VIS as a continuous predictor. That's not optimal. It's a count variable. There are different models that count for count variables that would probably be better. Smoothing procedures addressed DA2 poorly as an outline value. Although we should probably go through, check that record to make sure it's okay. Didn't eliminate extreme values for depravity. So value, reevaluated value, value of 60 for D1, Eudialis did kind of bring things in. Basically, we're looking at equal distance between the next 3 largest observations. So here the argument is further smoothing procedures risk obscuring potential influence of a rare but high values on a dimension of interest. Like I'm assuming if I'm doing in psych and law, folks can tell me like you probably don't have like really like Netflix documentary style like stuff cases, but you probably want to have those like in there to see like, boy, when this happens, what goes on with things. So we're wanting to kind of bring it in, but not smooth it down so much that sort of maybe we sort of lose stuff. So This is where we're just saying, what we've done. Analyses may proceed with continued monitoring of extreme cases for depravity. BIS delivery unbalanced but not overly problematic given adequate coverage of the cells. In addition, verification of entry and continued monitoring might consider models better equipped to deal with count data, right? Again, always thinking about level of measurement and sort of what goes on. We treat a lot of stuff as continuous, probably more often than we should. And at one point in our history, when we didn't have access to good programs and computing power and things like that, those were pretty fancy and niche models. But now with M+ and R and sort of other packages and sort of height capacities and SPSS and things like that, it takes a little bit of homework on your part. But again, there's nothing in those count models that you should be at least familiar with sort of the stuff that we learned here. So if you wanted to go through and do that, you could, and then maybe go through and take a look and see, does it make any difference? If it doesn't make any difference, then just sort of report your logistic model because it's more simple and more straightforward. People are going to understand it. Probably, right? But so screening for this is pretty streamlined. The only thing kind of new that we're doing is adding in checking for linearity of the logit. That's pretty quick and easy, and we're cutting out a whole bunch of other stuff too, just because these are really nice models, right? So really the only critical things that we're looking for are extreme values, collinearity is no good, linearity of your logit, and coverage. But we're still going to go through and take a look at distribution just so we kind of know what's going on with our data. All right. Questions about the screening process? Okay, cool. Let's go through, take a break. Come back 3:45. Zoom recording. Okay. So what we're going to do is we're going to go up to analysis, back to regression, down to binary logistic. Okay. We've got some of this set up already here. I'm just going to reset so we can start over. So sentencing, that's our outcome variable here. So we'll drop that. And then we've got centered impact, centered depravity, right? And then VIS delivery is our last variable in our model, okay? Then we're going to go through and we're going to go to categorical. And we're going to let SPSS know that VIS delivery is a categorical variable, so it means it's treated as such. And so then what we're going to go through is take a look at our reference group. So someone take a look at, I won't do it here because I'm kind of in the middle of stuff, but someone pull up VIS delivery or look at your handout. What do we want to have as our reference group here? What makes sense? None, probably. Right. So the first one. So here our reference category, leave that at first. But if I wanted to change things around, right, I could go through and hit last, go through and change that, right? So just making sure that you're very clear with these models. Like I said before, always critical to know what your reference group is if you're going to interpret things correctly. So here, our first category is going to be none. That's going to be our reference group. So we're going to hit continue here. And then we go through, hit options, and am going to ask for confidence intervals around my exponentiated variable. So this is just confidence bounds for my stuff. There's lots of other things that you can do if you get deep in the weeds with the logistic models that you can go through and ask for. We're not going to worry, we're going to keep it pretty simple with this. Okay. So you go through, hit continue there, and I'm just going to paste. Here is my logistic model. You go through and run this. bring this up here just because it'll be bigger and easier to see. Okay. But anytime you request any output in SPSS, you should be able to walk through and say like, okay, I know what this is telling me. Okay, here in your case processing summary, we're just looking at the number of cases included in the analyses, the number of missing cases, the total. Just want to make sure that that goes through and squares with what you've got in your screener, right? In the screener, we say we had 123 cases, is that right?
It's at 122, but.
Go to 122. Okay. That might have been.
Yeah, we said 122.
Okay, that must have got that wrong there. So Matt, can you shoot me an email, remind me to go through and check that? And just make sure that I'm sitting here. All right, but what we've got is matching up with our handout, so we're good here. Okay, so good, that was a flag. You go through and take a look, so make sure that we're in the right spot. Okay, go down through dependent variable encoding. Okay, want to go through here. We've got 0 is life, 1 is death. Okay, so life in prison is our reference group. Death is our criterion. What this means is what all of our output is going to be looking at the odds of death versus the odds of life in terms of our odds ratios and our interpretations. Okay, it doesn't have to be this way. We can flip things around, but things are going to start looking weird if you're not making sure that sort of things are set up the way you want to. Critical with these models that you always know who your reference group is. Okay. So anything that we're looking at, we're predicting the odds of death, the odds of a death sentence versus the odds of life in prison is what we're working through. Okay. Then we need to go through and we need to take a look at our categorical variables. Categorical variable coding. Again, this should look similar to the contrast that we did before. None is zeros across the board. Okay, so we know that none is our reference group. Our parameter for BIS delivery 1 is private versus none. 2 is Q&A versus none. 3 is open versus none. Okay, so again, because we can go through and we can have categorical variables in here, but to look at specific effects, we still have to go through and dummy code this. Or there are other ways of going through and coding it depending on what you're trying to do. You just want to make sure that whatever you pulled SPSS to do, you understand and it's consistent because it's again critical for all of your interpretations. Okay. Do people see what we've done here with categorical variable coding and how that's played out? Okay. So now we got into this piece, our beginning block. This is our classification table. Okay. Any idea on what's going on here? So basically what this is doing is it's with just an intercept model, this is classifying people or predicting whether people are classified as having life in prison or death sentence. What's happening with this model? Is this a good model? We're making a lot of errors in this model.
Like,
I think so. Okay. So here is what's actually going on. Whether or not people receive life in prison or receive the death sentence. Here's what our model predicted. What did our model predict? What's that?
like in terms
What's going on, Allison?
it predicts everyone gets the death.
It predicted everybody got death penalty. Okay. Why did it do this in a model with no predictors?
Yes, but is death coded 1?
Okay, death is coded 1. Okay. That doesn't actually affect it. In our sample, what's more common, life in prison or death sentence? Death sentence. So in the absence of predictors, who do I just what's my guess best for any case that comes up? I just predicted death sentence, right? And here it's saying that I'm right 57.7% of the time, right? better than half, but that's just a straight up consequence of imbalance in my model, right? So here, we've got 52 people who received life sentences, 71 who received death sentences. My model predicts everybody gets death sentence just because in the absence of any predictors. This is basically like guessing the mean, right? And so 57.7% of the time we're right? But this starts to get into a base rates, right? Like what happens if we had 5 people with death sentence and 300 with life? Then we just guess life and we'd be almost perfectly accurate, right? But is that a useful model? No, it's not telling us anything, right? So this starts to become one of those things we have to start thinking about base rates as well. Okay. Here it's relatively balanced. It just tips over to what's more likely. Death sentence is more likely. So my baseline model without any predictors, just guess that everybody gets the death penalty. Okay. Someone have a question about this? Yeah.
I think I'm just a little bit confused what the numbers in the output mean. Like I'm confused by like the 0 and 52 and the 0 and 71.
Okay. This is just a 2x2 contingency table. Here is what actually happened. Here's our observed. So we have life, we have 52 people, death, 71 people,
Okay.
right? But the model predicted no people received life across categories. Everybody received death penalty, and so that's where we've got stuff, right? So percentage correct for life, 0, because we didn't actually predict anybody got a life sentence. 100% correct in terms of death penalty, because we captured everybody who has a death penalty, but overall 57.7%.
Okay.
People sort of understand this table. Again, thank you, Evan, because it's critical that you understand these tables and what's happening with this. Okay. So within our logistic regression model, remember we talked about building models, and Johnny, some of the regression classes that we've talked about a lot of is like comparing this model to a different model. This serves as our baseline model. If we have nothing else going on, how does our model perform? Well, it performs, I don't know, not great, but we get more than half of our answers correct, right? So here, down here, this is our variables in the equation. Note that this is all under block 0. Block 0 is our baseline model, okay? Variables in block 0 is just our constant, okay? And what this is giving us, we'll see that we've got here my coefficient. This is my log odds. Here's the standard error. Here's my Wald test, okay? Here's the degrees of freedom. Here's my p-value, and here's my exponentiated function, okay? This right here is simply just giving us the odds of death versus life with no predictors, okay? So if I'm looking at this odds ratio here, this is my log odds, right? And so what I would say, we would interpret this just the same way we would interpret anything else. We would say for each unit, well, no, not unit increase, because this is a constant. Scratch that. This is just what it is. The log odds are just 0.331. What this says is based in this model with no predictors, what we're seeing is the odds of death are about 1.4 times greater than the odds of life with no predictors in the model. Okay. We could also say within this data set, the odds of death are sort of in this set, inmates are 40% more, or defendants are 40% more likely to be sentenced with death versus life in prison, right? This is just giving us an odds breakdown of just base rates in our model here. We have no predictors. Yeah.
People are 4 times more likely to.
1.4 times.
Oh, got it.
I'm just rounding that. So just 1.
Yeah.
Okay. Yeah.
Can you repeat what the constant means?
Constant is just base rate. So like we're just looking at the in this set, we're looking at the odds of death versus the odds of life. Okay. I mean, this is just basically what's in your set, right? So absent any predictors, what's happening with stuff here. Okay. And this is your log odds, but if we go through and exponentiate this out, we get our odds ratio here. Questions about this? Okay. So And again, we're just interpreting that odds ratio like any other odds ratio. We can say the odds of our criterion are 1 point, sort of blah, 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 or whatever times the likelihood or the odds of our reference. Or we can subtract that from 1 and think about odds greater than 1 are suggesting an increase, odds less than 1 suggests are indicating decrease in odds. Yeah,
One more question, sorry. How do we interpret the B again, you said?
the B,
Yeah, like.
this is just the log odds. So this
Oh,
is just is what it is.
And then what does that tell us? Sorry.
Don't worry about this. This doesn't tell you much of anything outside of just looking at your exponentiated function here, telling you what the odds of light in this data set, what the odds of defendant receiving a death penalty versus life imprisonment. All right, so then we go down through and we take a look at this. This is variables not in the equation. Okay, what this represents, this is giving you, you'll hear this called a score test or your Lagrange multiplier. Remember that we talked about for our logistic regression. It's a little bit weird because we don't just have one test for our individual predictors. We've got like 3 different tests that we go through, right? Remember we talked about our Wald statistic or our Wald scores. These are, which is what this is right here. This is what SPSS provides us, but it's actually not precise. It's not a great test of our end of anything. It's kind of an approximation, right? We also have Lagrange multipliers score test. That's what this is kind of giving us. And then we've got change in model log likelihood stuff, right? So we got 3 different ways you could go through and actually test the contribution of individual predictors. Okay. What this is doing is this variable is not in the equation. This is just your score test. And basically this is, you could use this to go through and say, all right, do I have evidence for an effect of impact statement, depravity, BIS delivery overall as a full model. And then here for our individual ones, this is going to be private versus none, Q&A versus none, open versus none. Okay. We're not going to spend a lot of time with this. This is not sort of but I don't know why. This is typically not what people will report, but it is a different way of going through and looking at stuff. This is better than Wald, even though Wald is what people will generally report. Change in log likelihood is the most precise way. This is kind of an intermediate, but this is what's going on in this set of the model. Yeah.
So that, can you help me understand like what that output is, I guess, testing?
Yeah, this is testing your individual predictors, Johnny.
Okay.
Yep.
Okay,
But we're just gonna ignore it for right now, just because people tend not to use this as the test.
so it would like, it's testing like that in a multi,
Yeah, everything
Fashion.
together. Basically, like, so what would happen if this variable were removed from the full model?
okay,
But in a different way that's different than the log likelihood test that we're gonna
deal, okay, thank you.
Would you prefer that we report the Wald in our column set, even though that's not the most?
I'm gonna have you do both. What I'm not gonna have you do is report Lagrange multipliers. Just because that's not what people tend to report. I don't know why not. This is just giving you a different look, okay? And so again, your Wald test is generally fine. It's just when you start to get at stuff that's, basically it's like your Sobel test. It's not perfect. It doesn't perfectly map onto the distribution, so it's not precise. So like Sobel's probably gonna be fine-ish, unless you have something that's kind of right on the edge. And so then but like sort of, it's kind of a similar situation there. So I'm just telling you what this is so that you know what it is, not for you to go through and pay a whole lot of attention to it. Okay. So this is our block 0, our beginning block. Then we're going to go down to our block 1. Okay. Logistic regression sets this up kind of as if it were a hierarchical model, which it kind of is in the way it's set up. You can go through and include things in other steps too, to go through and do stuff. We're not going to do that here, but it's certainly something that you can set up. Okay. Here, what you've got in your overall test. What this is giving you, this chi-square, this is gonna be the reductions in your model log likelihood given the inclusion of your predictors. Remember that we talked about in lecture. What you get for a logistic model, you get a -2 log likelihood value. And it's just kind of like a big variance component in that it doesn't mean anything if you just look at it. But what we can do is we can use that value to start to look at the contribution of different sets of predictors and things like that. Okay, so what this is doing is this is giving you the reduction in model log likelihood given the inclusion of predictors. So what this is doing, what SPSS is doing, is it's giving you, it's taking the log likelihood of a model with no predictors. And then it's taking the model log likelihood of the model with the predictors that we specified. It's looking at the difference between those two and then testing against a chi-square. Okay, and if we go through and we take a look at this, so the question here is, does the inclusion of depravity, BIS, and delivery method contribute to the prediction of life sentence versus not? Okay, and if I look at here, we're looking at step 1. I mean, they're all the same because we just dumped everything all in at the same time. And it's saying that, yes, we do have evidence that the inclusion of this set of predictors does in fact improve our overall model log likelihood. So our model fits better with these predictors as a whole than without. Okay, so you can kind of think about this as analogous to in your multiple regression, your test of your overall model. That's kind of what's going on with this. People sort of understand sort of this piece of things.
Could you repeat it so it improves, like the inclusion of these predictors improves the what?
Your model fit.
Okay,
Right. Specifically, it's your -2 log likelihood.
okay.
Okay. Your -2 log likelihood is just your, again, I can't look at a number and tell you if it's good or bad. It's just a number, but I can compare that to the -2 log likelihood of a model with or without sort of different predictors. And that starts to give me a very precise test of individual contributions. Yeah, Johnny.
So we look at the line with, like model
Yeah, well,
to identify
just look at your step here.
the step.
They're all the same, right?
Okay.
If you start sort of layering things in a hierarchical fashion, then those things will change, right?
Okay.
For just simultaneous stuff, they're all be the same, so you don't have to, they're all telling the same.
Okay.
You kind of get what's happening with this? All right, then we've got our model summary, okay? Our model summary, this gives us our actual -2 log likelihood, okay? So this is nice. This is the value of this model with our predictors in here, right? So this is our log likelihood value that we talked about in lecture, multiplied by -2. If you do that, it puts it on a chi-square distribution, and we can use this to compare different models, okay? So this is the log likelihood value of my model with 5 predictors. Is that right? Yep. So I've got my 2 continuous and my 3 dummies. So I've technically got 5 predictors in this model. I've got 3 predictors, but the way it's coded, I end up with 5. Okay. And so this is telling me my -2 log likelihood for the model, right? This is being compared with here, what the model is without that, with the no predictors. So this was the difference between my base model log likelihood and this value gives my 20.592, 529, it's 5 degrees of freedom is giving me, so this p value here. Okay, so this right here, looking at the model summary, this is just giving you your -2 log likelihood for the model. Here you have pseudo R² statistics, ignore those, okay? They're not typically, I mean, there's something that people have come up with, but they're generally panned, they're not super useful. People certainly don't interpret those as proportion of variability in the model. Go ahead and ignore those. Know what they are, but you don't have to look at them or worry about it. Yeah.
So this value that we have for the -2 log likelihood, we have compared that to like a model that essentially has like no predictors in it, and that's how we theoretically get like the 20 point.
Perfect.
Okay, thank you.
Exactly. Yeah, SPSS doesn't give you directly your -2 log likelihood for the intercept model, but you can use addition to get there. So, going down through, we've got a new classification table, okay? What's going on with this classification table here? Okay,
Looks like we're predicting a little bit better.
yeah, before we just guessed that everybody got the death penalty. Now we've got predictors in the model, so we got a little bit more variability, right? And so what we can do is take a look at this and look at this in terms of true positives, true negatives, false positive, false negatives, right? So here we have 29 people who were predicted to get life in prison, who did get life in prison, so we're good. We got a true negative here, right? If criterion is death penalty, we've got a true negative, and then we got 56 true positives. Our model predicted 56 people would receive death penalty. 50 of these people did, so we've got a true positive here. Okay. Now here we on the other diagonal, we've got some misses. Here we got 15 people who got death penalty, who were predicted to get life in prison. So we got misses here. So we've got a false negative. Okay. Here we've got 23 people who were predicted to receive death penalty. They did get life in prison. So we've got 23 false positives. Okay. So here, if we're looking at overall percentage, we're at 69-1. Right? What were we before? 57 something, right? So we're seeing that overall, there's an improvement in the prediction of like a functional, like something that we can see in terms of prediction of functionally whatever outcome that we're taking a look at. People see what's going on with our classification table here. And this is what we can go through with this. Then we can go through, start cranking out specificity, sensitivity, sort of positive predictive power, negative predictive power, some of those types of things to start talking about qualitatively how well our model is doing with things. Okay. All right. Questions about this? Still good, doing fine? Okay. So we've got some incremental improvement in terms of our overall model, right? Just looking at our classification table, looks like our model of predictors is doing a little bit better than our model of just guessing the mean essentially. Okay. Now we go down through and we take a look at our actual regression table. Okay. So this is a little bit different. Wanting to go through here, we have our values for our continuous impact, or the value that we're treating as number of impact statements that count, but we're treating it as continuous impact, continuous depravity. But then we've got things a little bit different. We have our BIS delivery. This is our categorical variable, right? And so what we'll get is you'll get kind of like an omnibus test of your categorical variable. Overall, it looks like the BIS delivery is contributing to this, it's making the model better. It's improving the model based on my p-value, okay? But in order to see how that's sort of improving, what we've got is our three dummy codes here, right? This is open, is that right? No, private versus none, open or Q&A versus none, open versus none, okay? So again, critical that you know how these contrasts are set up, okay? So if I go through and take a look, here I have my effect of, do I have evidence for an effective impact? Danielle, are we seeing any impact or evidence here for impact? No, it's not, right? It's p-values nowhere in the vicinity of anything that we would identify as interpretable. So it looks like, at least in this model, when we're accounting for depravity score and BIS delivery, it does not appear that the number of impact statements has anything to do with determining life or death. Okay. So we go through and don't need to worry too much more about that. But for our depravity score, Danielle, are we getting evidence for our depravity score? Yeah, it looks like depravity is contributing to the model, right? Is depravity when we're controlling for or accounting for impact statement BIS delivery, it looks like depravity score does contribute to the odds of a death sentence versus life in prison, okay? So going back to B, Mandy, you want to know what B is? B is our log odds. We interpret our log odds the same way we would interpret any other thing. If I looked at this, I would say, well, what we're seeing is that for every unit increase in depravity, in center depravity score, we're seeing a 0.096 increase in the log odds of death versus life in these data. Okay, does that mean anything to you? No, it doesn't mean anything to me either, right? Because it's log odds. It's a weird transform of that outcome. It's a transform of probability, right? We can get to probability, but it takes some math to get there. And so what we can do is we can go through and take this and we can exponentiate this out to get an actual odds ratio. Okay, and so EXPB right here, this is our odds ratio. This is what we're going to typically interpret within the context of our logistic model, right? So what we're saying here with this is I guess, so we've got an odds ratio of 1.1. What does this tell us about the odds of death versus the odds of life for every unit increase in depravity score? Is it getting bigger or smaller? It's getting bigger, right? So the odds of me getting the death penalty increase, the odds of me, and this is all, you always have to make sure that you're sort of referencing what the reference group is. So the odds of me getting death penalty versus life in prison increases with every unit increase in depravity score. Okay. Let's put a pin in that and sort of move on to something because this starts to get a little bit more tricky with continuous predictors. Okay, so but we just know that we have the depravity score contributes to an increase in the odds of life in prison, or excuse me, the odds of death sentence versus life in prison. Okay, so let's go down to our BIS delivery. BIS delivery, we know contributes, so we're saying okay. But if we go down through and Olivia, take a look at our individual codes, what seems to be driving sort of this BIS delivery as a contributor to our model?
When you compare the first one, which was then
Private, actually.
private compared to our reference group, which was none.
None, right? So of this categorical variable does look like it contributes to the model. But basically the way we have this coded, at least in this dummy code, it looks like this is mostly coming out of the comparison of private administration or private delivery of BIS relative to not at all. And then we see that we do have an effect here, okay? So again, if I go through, Mandy, if I would just wanted to look at this, I would say in the comparison of private versus none for VIS, right? What I see is the log odds decreases by 1.5 units for those individuals delivering a VIS in private versus not at all, right? That doesn't mean anything because, like, I don't know about log odds, right? But what I can go through is I can exponentiate this out, right? And I get an odds ratio of 0.22. Okay? What does that say? Is administering a BIS in private versus not at all, does that increase the odds of death versus life, or does it decrease the odds of death versus life? Decreases the odds of death versus life, right? This is where we start to go through and need to have a really strong understanding of odds ratios here, right? So basically what this says is with an odds ratio of 0.22, we would say, one way we could talk about this, we could say that the odds of death are 0.22 times as likely as the odds of life in prison for cases where a VIS was presented in private versus not at all. Okay.
Can you say that again?
Yeah. We say the odds of death, the odds of a death sentence are 0.22 times as likely as that of life in prison for cases where VIS was presented in private versus not at all. Which is technically correct and a fine way to talk about it, right? The weirdness is we're talking about something that's 0.22 times as likely. which actually means when we hear that, we make something, we make it's gonna be more likely, that actually indicates that it's less likely, right? So we could flip this around, right? And we could talk about this as the odds of death versus life decrease by 76% for VIS presented in private versus hospital, right? Basically, what we're doing is we're just flipping this around, right? If we take 1 minus 0.222, right? I guess that should be 78%, maybe. Is that right? Yeah, should be 78%. Okay, so basically what we're saying is changing this around to talk about this as a decrease in odds, right? So we're saying the odds of death versus life decrease by 78% for VIS presented in private versus not at all. Okay. There's just, the thing is with these odds ratios, there's a lot of different ways you can go through and interpret them in ways that make the most sense in terms of communicating something. So wanting to have a strong understanding of what this means and how to go through and present it, I think what your audience is going to really understand. Yeah.
This is the one where if it's an increase, it's that number minus 1, right? Correct.
What's that?
If it's an increase like 0.22 minus 1.
Well, that would give you a negative.
Yeah.
So one and one is
Yeah,
even
if
on
it's
this,
like-
right? Yeah, yeah. So if this was 1.22,
Yeah.
we would say let's say it was 1.22, right? I could say that the odds of death of a death sentence versus life in prison increased by 20% for people who give a VIS in private versus not at all, right? But this is a little bit tricky because it's the opposite. We are actually seeing, and I'm assuming for psych and law folks, this is kind of weird. Like you would expect the delivery of a VIS to result in an increase in life or a death sentence versus life in prison.
Not if it's like.
Really? Okay, so
Cause then it's right, it's not being done in front of like.
Yeah, it depends on the delivery method and what type of case it is.
okay. So at least here, and again, like any regression model, we're saying if we account for all these other factors, right? If we account for the number of impact statements delivered and the overall depravity of the case, right? What we're seeing is that presenting this VIS statement in confidence in private actually reduces the likelihood of a death sentence by a fair amount, close to 80%. Do people see how we sort of arrived at that with sort of looking at the odds ratios here? Okay, cool. So let's go back to our depravity score here, because here we do have a positive odds ratio, right? Suggesting that as depravity scores increase, what we're seeing is an increase in the likelihood of death sentence versus life in prison. Okay. Someone want to take a crack at interpreting that odds ratio for me?
So the odds ratio.
Yeah. For depravity here. Odds ratio 1.1.
Try. I
Yeah,
think
go
I'll
for
get
it.
it wrong, but. So for like every 1 unit increase and depravity. The odds of a person getting the death penalty is the same as a person getting life sentence.
Close-ish. You're getting there, Lindsay.
So it'd be the same except it's not the same, it's a 10% higher likelihood of the death penalty for every 1 unit increase.
Versus,
Versus a life sentence.
okay, and this starts to become critical when we're doing, like, you always need to make sure that people know what the comparison is, right? So Lindsay's exactly correct. What we would say is for every unit increase take that away, not for every unit increase, for a unit increase in depravity score, we would see a 10%, we would expect the model is predicting a 10% increase in the odds of life versus the odds, or the odds of death versus the odds of life. Okay, so it's a lot of things to sort of keep straight in your mind. Okay, so 10%, does that seem like a lot? Doesn't seem like a lot, right? 1.1 odds ratio, it suggests an increase, but it's not super big, okay? What's maybe the caveat to this?
Can I ask where
Yeah.
you get the 10%? Is that from the wall?
Nope, it's right here. So remember
Oh,
that
it's,
even odds is 1, right? So if I take even odd, if I take 1.1 minus 1, I'm left with 0.1, it's 10%. What do you think, Jeff?
You repeat the original question.
Yeah, so it looks like if I'm just looking at this, an increase in odds of 10% or an odds ratio of 1.1 doesn't seem like a whole lot. What might start to provide some context around this?
Yeah, well,
Okay, life or
if you
death.
have like a really high gravity score.
Yeah. Here, we got dummy codes. It's just a comparison of this group versus that group, right? Depravity score, what's the range of our depravity score?
Yeah, 100. You're doing 100.
Yeah, I mean, like, we pulled someone into like 60 who was way off of there. Is a 1 unit increase in depravity a meaningful increase in depravity? Probably not, right?
But it's got a lot of increases.
But if you got a lot of increases, right? And can someone remind me when we're talking about logistic models, what happens? Like, are we working on the same scale as like our standard regression models? No. So if I say not a unit increase, if I say 2 unit increases, is that just an additive function there? Yeah, it's all of this is a logistic model, right? So what we're doing is we're working with, what we're actually doing is we're saying 1.10 times 1.10, right? What's that number? So tell me what that is.
Wrote it in a spot where the light hits the board.
Oh,
1.21.
1.2. So basically, it's 1.1 times 1.4. What does it do?
1.21.
Can you see that?
Yes.
Okay, so here's the odds ratio for a 2-point increase, right? And now we would say that for a 2-point increase, we would expect a 21% increase in the odds of death sentence versus the odds of life in prison. Okay, but if I go through and I take a look at what a standard deviation is on this, that's 8 units about, right? So now I have 1.10, the 8th power. What's that? Check that again. Is that right?
Yeah, 1.14, yeah.
2 point what?
1435.
Only so 4. Rounded to.
Okay, yeah. Actually do this for me. What is 1.10 times 8 point, or to the 8.19th power? Do that.
8 point what?
8.1.
0.19.
2.18.
Yeah, 2.18.
Okay, that's where I was, okay. 2.8. The 8.19. So I'm just taking that to a standard deviation increase, right? And so if I do that, now all of a sudden what I'm saying is for a standard deviation unit increase in depravity, that would be associated with 118%, about 118% increase in the odds of death versus life in prison. Okay, so what we're doing is we're sort of exponentially sort of creeping up this scale as a function of this, as a function of increases here. So even though, and this is just like a regular old regression model, just because this is associated with a 1 unit increase, a 1 unit increase might not be all that aggressive. But if we go through and start adding things on, the only thing with the logistic model we're taking that increases to hours as opposed to just additive function, and so things can get out of hand real fast with this stuff, right? So just always use, this is something we should always be thinking in terms of interpreting the practical implications of our regression models, right? Particularly if we've got fine-grained predictors, but particularly here for our logistic models, we've taken that to an exponential level. So just being very careful that you recognize what's going on. Categorical differences here, these are easy. This is just a straightforward interpretation, right? The odds of death for the odds of death versus life in prison for folks who present BIS in private are about 0.22 times that of odds of death versus life for people with nothing at all. There's only one unit that we can go through and do, but here with our continuous predictor, go quite a bit with that.
What was the number you said?
What's that now?
What was the number you said for people who present BIS in private is?
0.22 times.
All right.
We'll kind of understand the interpretation of the model, what's going on with these and how we sort of can start playing around with odds ratios. Okay, I went through and it was an email that I sent to like several years back to a class, just kind of laying all this stuff out, and I just copied and pasted. My God, it's a fine handout. Go through, take a look. Want to be very, very solid on your odds ratios, understanding and being able to play around back and forth with how we go through and interpret these. Okay. All right. So last thing that we're going to do, remember that like all of this, we're basing all of our assessments on our WALT test. And a WALT test is fine, you know. But if I had something that was like 049 or 056 or something like that, the concern is that WALT is not precise, right? I'm not sure, it's what everybody reports, but it's just, there are better ways to go through and do things, right? And so one of the ways that we could go through, we could start to go through and play around with this model, okay? So let's go back to our data and let's go to analyze and let's go to regression, go to our logistic model, and let's look at a model that just has our centered impact and our BIS delivery. Okay. So I just went through, so we just got a 2 predictor model, which actually turned into a 4 predictor model. So we got to break those up, right? And then I'm just going to go through and run this. Okay. So again, this model is the same thing, the same model as we have sort of before. But this is just a model that just has my 2 predictors. Okay. And so if I go down through and take a look at my my omnibus test here, right? What I end up with is a model log likelihood of for my overall model summary, my -2 log likelihood is 156.318. Okay. And this is my model log likelihood for a model with just my 2 predictors. This is the model without a depravity score. Okay. What was the model with what was my overall model? What was the log likelihood of my model with BIS predictor and with BIS as a predictor, my full model?
47.
What was it?
147.038.
Okay. Here we've got Olivia Mesa, can you see that here? So this is log likelihood of a reduced model. Log likelihood of my full model. Okay. Which one of these is the better log likelihood?
The 156.
What's that?
The 156.
that right? Which one, Kate?
The full model.
The full model, right? So a lower log likelihood is what we're looking for. A smaller log likelihood is better. Smaller log likelihood indicates better fit. And so what we see here is with our model with two predictors. And our model, so 4 predictors. And this is our model with 5 predictors. People see where I'm getting 4 and 5 predictors with this? Okay. What I can do, what's the difference between these two models? What's the variable that I've omitted? Depravity, right? What I can do is I can subtract these two values to get a value of 9.28. And when I subtract these model log likelihoods, this is distributed on a chi-square distribution with the degrees of freedom equal to the number of, so the difference in the number of predictors that I have here. So this is distributed as the -2, the difference in my -2 log likelihood is distributed as a chi-square with the degrees of freedom equal to the difference in the number of predictors, okay? So I've got 9.82, right? Which is gonna be equal to a chi-square distribution with how many degrees of freedom? 1 degree of freedom. Okay. And so if I go through and I test 9.28 against a chi-square with 1 degree of freedom, I need a p-value equal to 0.0023. What does that tell me about the contribution of depravity to this overall model? It's important, or at least I would be careful with important. It at least statistically improves the model. Okay? I have a better model with depravity score in there in terms of gauging like the statistical fit of my model relative to a model without. Okay, now if we go through and we take a look, someone tell me what was the walled p-value for depravity in my full model? What is it?
0.39.
Value for depravity?
What's that?
The p-value for depravity in the overall model.
Oh, 0.011.
0.011, right? So here we've got a more precise test here of that contribution. Okay. So what we can do for individual predictors, similar to things like when you're playing around with your hierarchical model, what you can do is you can run a model with all your predictors and then run a second model without that predictor in there and just compare the two negative log likelihoods, and you can get tests of those individual predictors. SPSS doesn't do this for you. I'm not sure why. I'm fairly certain you could code that quite easily. What it does give you is Lagrange multipliers, that score test, which is a version of this, but not as good of a version of this, right? So again, one of these situations where if you have something that's kind of on the margins, right, where walled is kind of ambiguous, right? It's in that 045, 055 area. So what you can do is go through and run this and actually look at the contribution, the statistical fit of your model with and without that predictor, and get a much more specific p-value than what you're getting in your output. Okay, people see how that worked? Same thing, we could go through on this. And again, if you go down through and you take a look at your overall classification with a model without depravity, it's 67.5 was your overall. Here it was 69.1. So it's a little bit better. It's not huge, but statistically we have very clear evidence that adding depravity in that mix makes for a better fitting model. Okay. Same thing here in this other part of the handout here. Here we have, this is where, this is just our overall model setup. Okay. But if I go down through and I take a look down here, you can compare what the individual predictors look like with and without, things along those lines, right? So just recognizing that with your logistic models, your overall log likelihood is your overall fit of the model. Okay. It's telling you, like, you can't just look at a -2 log likelihood and say like, oh, this is good or bad. What you can do is you can start comparing nested models, right? Could I compare a model with where I had omitted delivery method? My categorical variable, could I compare a model with and without BIS delivery method? Sure, I could, yeah, right? So I could go through and take a look at that. And what that would do is that would tell me the difference between a model where BIS delivery method is in there and with it where it's not. And I could go through and I could compare the -2 log likelihood there. But if I did that, what would I be testing the degrees of freedom on? How many degrees of freedom would be in that model? 3, I'd have 3 degrees of freedom, right? Because I just have one variable in there, but I've got to break it up so that it makes some sense, right? So then I would be testing that chi-square difference on it against a distribution with 3 degrees of freedom, right? I could go through and I could run a model with just depravity score and test that against a full model with depravity delivery and number of impact statements too, right? So lots of different ways you can go through and compare these. We're just comparing the overall fit of the model. So this kind of this nondescript number, but as that nondescript number gets lower and lower, we're seeing a better and better model fit. Okay, so go back through and take a look at it. We've kind of broken this up on 2 sides of a midterm exam, which is not an optimal way to do this, but go back through, having gone through and done this, take a look at those slides and sort of see some of this stuff start to crack and fall into place. Yeah.
Can you just clarify what a nested model is or what that means?
Yeah, it's actually pretty complicated, but for this, it just means a model where you got one model with a set of predictors and a second model with a different, smaller set of predictors.
Okay.
It just needs what I couldn't do is compare a model with BIS delivery and depravity versus a model with number, because those aren't nested. You got a different set,
Okay,
right?
that makes sense.
But basically, think about nested models as a stepwise regression. As I put things in or out, what happens to my overall fit?
Okay, thank you.
Other questions with this? Okay, feeling at least sort of in this vicinity of kind of understand what's happening with these logistic models. Again, very, very cool, underutilized models in psychological science, oftentimes because the thing that we're interested in isn't necessarily that dichotomy. Now, we can also take this model and extend it into multichotomous logistic regression, right? I've included a handout. We're not going to get into that in this class, but basically you're just, if you have a multi-categorical outcome, you can run through and do basically all this stuff. The only thing is basically you're setting that up in a series of logistic regression models where your outcome, let's say you have 3 levels of your outcome. It's just 1 target versus a reference, 2 target versus, it's just kind of stacking them all on one another, okay? But, so a lot to kind of go through and deal with, right? There's no free lunch, there's just a lot going on in those models. But have included a handout with SPSS where it's just like me walking through how to do this. If you ever have one of these models, Tabasco, they'll have a great chapter on sort of navigating this stuff. So if you understand logistic, straight basic binary logistic, you're going to be set up with a little bit of sort of studying to pick those up as well. Awesome. Okay. Let's go through and just jump into to close out today, just starting on some of the repeated measure stuff. Okay. This first part is all just basic, sort of getting you back into, to this point, we've just been working, we've done a lot of continuous models. What we need to do is transition back into start thinking about some means-based analyses, which are all expert in means-based analyses. So a lot of this first stuff is just basically all of this is just going back through and taking stuff from 50-60 and refreshing it in your brain and just starting to mix together repeated measures analyses with between measures analyses so we can go through and start to put these together in some interesting and creative ways. Okay. So remember going back, the basic structure of our ANOVA models is basically just a t-test, but we're just going through and we're expanding out the number of groups, right? So what we've got for our ANOVA is we're saying we've got population 1, population 2, population 3. I can't study these populations directly. What I can do is I can get good samples from those populations, measure whatever characteristic it is that I'm interested in, and then start comparing to see, are the differences that I'm seeing across these samples greater than what I would expect just based due to sampling error, right? So here we've got 3 samples of 15, we've got means of 23, 28, 20.8. And what we're interested in is, are these groups comparable in terms of whatever outcome it is that we're measuring? We've got samples that we're measuring, but we're really interested, our hypotheses are all about these populations. And do we have evidence for differences here? Okay, so a couple possibilities when we're seeing these differences, right? That these differences are the result of random fluctuation. The value of whatever we're measuring is actually identical across all of these populations. It's the same, right? And the differences that we're seeing here are just due to sort of random sampling error and fluctuations. Or it's also possible that we could be seeing reliable differences across these population values. If I could observe these directly, I would see that they were different, and that's what's driving the differences that we're seeing in these samples that we're pulling from people. Remember, this is sort of making sense. So our null hypothesis, again, is that mean 1 equals mean 2 equals mean 3, means the population from each set we're drawn are equal. We talk about this in associative language. We can say there's no relation between our grouping variable X and our outcome Y. Any of that's perfectly fine, right? We've been working with a lot of associated GLM types of stuff. This is all special cases GLM. We can talk about this any way we like, just giving us a little bit more flexibility. Our alternative hypotheses, we don't have a specific alternative hypothesis, right? These means could differ in any number of different ways. We're just saying that one population mean differs from the others, right? Or we're saying that the data are likely that these data, technically we're saying that these data aren't, the data that we're seeing are unlikely, assuming equal population means, right? We test this with our F, right? This is just the variance between samples over the variance expected if the null hypotheses were true. As that ratio increases, the differences that we're seeing, the variances that we're seeing across means starts to increasingly exceed what we would expect just due to random stuff. Our F statistic increases, and we're starting to get more evidence that, hey, maybe that against that null hypothesis. So again, here we've got 2 sets of data. Again, thinking about variance, again, as a proxy for differences, right? We've got set 1 and we've got set 2. Is there any good, easy way to win in a single number identify like, oh, mean differences across each one of these? No, because we've got, 1 versus 2, 1 versus 3, 2 versus 3, 3 versus 1. Hard to go through. If we start increasing the number of means that we have to compare, it starts to become hard. But what we can do is we can start to go through and look at the variance across these versus the variance across these, right? And Mesa, which one of these are we seeing greater differences or greater variability? Set 1 or set 2? Set 1, right? We're seeing more variance across these set versus these ones here. And assuming that these things are measured on the same scale, we're having greater evidence of differences here in set 1, okay? And so the objective of our ANOVA model is to start to parcel out this variability, to start to look at differences and section things out into between treatment variance and within treatment variance. Treatment just being the traditional ANOVA language for groups. And remember, when we're going through and we're seeing differences across groups, a couple of different ways, things that can start to come up with that, right? We could see differences, systematic differences in my mean values across these groups here due to just differences in the actual thing that we're measuring, right? So here we're looking at performance under different room temperatures. We've got 50 degrees, 70 degrees, 90 degrees, right? So the differences we're seeing in the number of problems solved, here we've got 1, here we've got 4 at 70 and 1 at 90, could be because there are real differences in terms of problem solving ability under these different conditions that are driving what we're seeing. We can also have random non-systematic differences, right? This is just individual differences, just random errors, experimental error, things that are going on. And we can also have systematic differences that are unrelated to the grouping factor. These are things that, let's say, everybody in treatment 1 at 50 degrees did these problems at 6 in the morning. And everybody in treatment 3 did these at 10 o'clock at night. And these are the folks who did them at like 2 in the afternoon or something like that, just because we set up a really terrible design. What we've got, what could be contributing to this is stuff that's not in the model, right? It's not random effects or random things that don't account for anything. There's actually something going on. It's just something that's not in the model, right? And any differences we're seeing due to a variable that's not in the model, what do we call that? Error. It's all error, right? So here, when we're thinking about why we're seeing differences between our groups, always thinking about the possibility of some systematic differences, could be random stuff, or it could be stuff that we're just not accounting for in our model. Ringing bells, making sense? Okay. And if we go down through, where are we seeing between group differences in this set of data? What's that? We're seeing differences, right?
Yeah.
But down here, sort of across group, this is where we're looking at those group differences there. We can also go through and separate things into within group differences. Here, what we're doing is if my experimental condition or my grouping variable is the only thing that determines a score in terms of whatever I'm looking for, if that were the case, what should everybody within a group, what should scores within or everybody within a group look like?
Same.
They should all be the same, right? But they're not. We're still seeing people in the 50 degrees performing a little bit differently, people in 70 reporting a little bit differently, same thing in 3, right? So these can't be, if they're all happening within a group, it can't be due to temperature, it has to be due to something else, right? Now, these could be due to individual differences, they could be due to experimental errors, right? But they're happening for something that's not, we haven't accounted for in our model. So by definition, this is error, right? And so here we're saying within these groups, this is all stuff due to reasons that we don't understand. It could be random stuff, or it could be some sort of systematic thing that we didn't account for. Who knows, but it's just error. So what we're doing in our ANOVA with our F ratio here is we're comparing these two different types of variance. We've got between treatment variance. This is the stuff that's due to systematic differences, hopefully, versus our within treatment variance, which is just due to sort of random whatever stuff. And so conceptually, we can think about this as observed differences over differences expected if these were all drawn from population with equal value. So we can also think this as systematic effects versus random differences and other stuff versus random differences and other stuff. If we've got evidence for an effect, if we've got no evidence, if it's entirely due to sort of just random errors and things that we haven't included in our model, then the differences that we're seeing between groups is probably going to be about the same as differences we're seeing within groups, and we're going to get an F ratio that's very close to 1. But if we've got random differences across groups and random differences within groups, but then we've also got some systematic effects here, hopefully we're going to get an F ratio that starts to increase, is larger than 1, and we have evidence for an effect. Is this all clicking and back? Okay, remember this, so all this is making sense for the new level stuff. All right. So our ANOVA stuff, sum of scores total. This is the total variability in our scores. It's how we go through and calculate this. This is the sum of the squared deviations of individual scores minus the grand mean. That's our overall variability in our model. We've got our sum of squares error. This is our variability within each group or condition, right? It's variability within groups due to individual differences, errors. Here we're taking some of the squared deviations of individual scores subtracted from the group mean, right? So here's my individual scores minus my group mean. Some of those squared deviations gives us our sum of squares error. Our sum of squares treatment. This is the variability of the differences that we're seeing across groups. We can get this by subtraction. We can take the total minus the error, gives us treatment. Or we can calculate it directly by looking at the sum of the square deviations of my treatment mean minus my grand mean squared times the number of people that I have in each sample, right? Assuming a balanced design. Mean squared, remember that mean squared is just a fancy ANOVA term for variance. That's all it is. We're taking mean squared for treatment is the sum of squares of treatment divided by the degrees of freedom. Degrees of freedom for treatment gives me a variance term. Mean squared for within sum of squares error divided by degrees of freedom, same thing. Okay. F is mean squared treatment over mean squared error. And this is how we go through kind of for all the stuff together. People remember kind of pulling this together last semester from the fall, kind of where these different components are looking at. So the understanding the logic behind the scenes for our ANOVA stuff. Okay, cool. So again, we tried previously for a stint where we had students back, boy, you know what, we're coming off of fall where we're doing a bunch of means-based analyses. What if we just do means-based analysis stuff first and then go into the regression stuff, which seemed like a good idea. Like, yeah, let's go through and try that. Actually, it's a bad idea. Like it's true off the whole flow of the course because we jump right in the middle of something that gets super intense. And I would say for learning purposes, forgetting stuff and then relearning it is a valuable part of consolidation. And so having taken a break from regression, so understanding sort of all of that stuff and then coming back to this, hopefully we'll go through and help re-solidify some of this stuff. So again, with our mixed factorial designs, we're just going to be, it's just going to be a marriage of our between groups analysis and within groups analysis. Well, the way we can do is start to put together studies that map very closely onto really interesting questions and start to become incredibly powerful, right? Which makes it great fodder for dissertations, theses, outside projects, things along those lines. Anytime you incorporate a repeated measure into your analyses, it's in your best interest to do so if you can make that make sense. And so what we'll finish up the bulk of our stuff is working through these repeated measures models. A lot of it's going to be stuff that you already are familiar with, or hopefully are familiar with from last semester. Just kind of adding in the layer. The tricky part starts to become once we have our omnibus effects and we can say, oh yeah, we've got essentially a moderated effect, right? There's some between group factor that's changing the pattern of mean that we're seeing across time. The hard part then becomes going through and figuring out where that could be, because it could be in a lot of different places. And the story that you tell will be largely depending on how you go through and try and approach this. So want to be thinking flexibly with that. Okay. All right. Thanks, everybody. Nice work. We're getting close to the end, but we're in a good spot. If you have questions or want to go back through and take a look at that midterm, just let me know. I'm happy to sit down, walk through where things were you did really well, maybe where you got a little bit off base, so to make sure they have that covered, or if you look through it all makes sense. The light bulb moment, fine too. But I'll go through, get the logistic stuff posted, give you groups, and we'll take things from there. Okay, awesome. All right, we'll see you, everybody.